Okay, Kirchhoff's first law, this thing, current going into a junction is equal to the currents going out of a junction, and they're summed, not multiplied. So I1 equals I2 plus I3. Now if there were more branches, depending if it's going out, then you'd add it on this side. If it's going in, you'd put it on this side. So currents going in equal the sum of the currents going out. Now this is derived from a rule, conservation of something. You know what it is? It's conservation of charge. Okay, Kirchhoff's second law, this thing, the sum of EMFs in a loop is equal to the sum of potential differences in the loop. Okay, so this is an EMF, this is an EMF. There's going to be a potential drop across this resistor. There's going to be a potential drop across this resistor. So first thing, we got to pick a direction. We're going to go this way around. Now current is going to go this way. It's just a convention. If you choose your current this way, and in your final result you get a negative number, it means current is actually going this way, but it doesn't matter. You just have to keep the same direction. Okay, so to form our equation, let's start from here. EMF or current is going to be driven this way, and it's the same direction as the loop direction. That's going to be a positive term. E1 is our first term. And now we go to the next item. This resistor, current is going through this way, and our loop direction is also that way. So it's equal to I R1. Same thing for this resistor. Current is going through it this way, and the loop direction is going this way. So we can just add that. Now this component, current wants to be driven this way, but our loop direction is the opposite direction to that. So it's going to be a minus term. So that's the equation for this loop. Now if you had a branch system, let's just do one resistor. And you're doing this loop, just pretend that stuff's not there. If you're doing the entire thing, pretend this junk in the middle isn't there. If you're doing this loop, pretend that junk isn't there, okay? For two loops, or the circuit drawn here, you can have three possible loops. This one here, and this one here. Now this law relies on another conservation, and it's conservation of energy. Now, they may ask some questions about ammeters and voltmeters and why the resistance is the way it is. So for an ideal ammeter, why is its resistance 0? So where do you measure current from? It's in series, so this is where our ammeter would be. Now we don't want any potential difference across it, and we don't want any current drawn from the ammeter, because that would affect our reading. So that's why it has to have 0 resistance. So there's no potential drop across it. Now for a voltmeter, it's going to have infinite resistance, ideally speaking. Well, where do you measure voltage from? It's across something, it's going to be in parallel. Right? So you don't want any current flowing through it, or else it would affect the reading. So you don't want any current flowing through it. So you're going to have very high resistance so that no current flows through it. Right? Now we're going to derive this equation. Our total equals R1 plus R2. Now you can imagine if there were more resistors in series, you just add more terms. So first thing to consider is, what is the same for this entire loop? Well, it's current. Current is the same. So B total equals the potential drop across this resistor and the potential drop across this resistor. So this will be V1 plus V2, V1, V2. Now what's a formula for V1? V1 equals I R1, V2 equals I R2, and for the total thing, V total equals I R total, right? So now we're gonna sub all that stuff into this equation. So you get I R total equals IR1 plus IR2. All the currents are the same, so we can cancel all of those. And therefore, we're left with R total equals R1 plus R2. So if you can imagine, if you had more resistors, there'd be another one here, there'd be another equation, and you just add them, right? So that's why R total is equal to the sum of all the individual R's. It's fancy notation, don't worry about it. Okay, so for in parallel, same kind of ideas. What is constant? Well, the voltage drop across it is constant. What is changing? Well, the current's going to be changing. So the current through this one is different from the current in that one. So I'll write that. I2, this will be I1. Now we have a junction here. So let's write that. I equals I1 plus I2, right? So that's similar to how we did this here. So now we're gonna have to come up with equations like this. So let's do that. So V is constant, so V equals, let's do this one first, I1 R1. V equals I2 R2. And the total resistance across it is equal to this right here. So let's sub all that information into here. First we need to rearrange these actually. So make I the subject, I1 equals V over R1, I2 equals V over R2, and I total is equal to V over R total. It's a bit small, I hope you can see that. So now we're going to sub that into here. V over R total is equal to V over R1 plus V over R2. Now all the V's are the same, so we can cancel those out, which is why the formula for resistance in parallel is this right here.